The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, let's get started. I once taught with a professor who was lamenting the fact that as the term progresses, attendance at lecture tends to drop off and gets pretty dramatic by the end of the term when you're lecturing and nobody's there. And I asked him what he did about it. And he thought about it and he said, there's only two things that can get students to come to lecture: candy and sex. Now, we've already tried candy, so today we're going to talk about sex. In fact, we're going to use graph theory to address a decades-old debate concerning the relative promiscuity of men versus women. Now, graphs are incredibly useful structures in computer science, and we're going to be studying them for the next 5 or 6 lectures. They come up in all sorts of applications: scheduling, optimization, communications, the design and analysis of algorithms. In fact, next week you're going to see how 2 Stanford graduate students became gazillionaires because they used graph theory in a clever way. But let's talk about sex. The issue that we're going to address today is one of the most talked about and most well-studied questions in all of human sociology. On average, who has more opposite gender partners, men or women? Now, opposite gender is going to be important, and by this I mean one boy and one girl. All right, I'm not making a political statement. It's just that the math is a lot easier that way, as you'll see. Now, I'd like to start by taking a poll here to see what you think about that. So raise your hand if you think men, on average, have more opposite gender partners than women do. Ooh, only a few. You can. Yeah, 1 on 1. Okay, so let's say over the course of their lives, or over the course of 2010, that men in America have more opposite gender partners than women in America, say in 2010. Raise your hand if you think men have more going on. All right, a bunch of you. Raise your hand if you think women have more opposite gender partners. Oh, this is unusual. Maybe even more voted for women, but it's close. Raise your hand if you think it's equal. All right, about the same. Raise your hand if you think there's no way to know, that it's hopeless to really figure it out. All right, nobody goes for that. Yeah, all right, good. All right, well, now in the popular literature, I think the feelings are different than expressed here. Pretty much universally in the literature, it's believed that men have more opposite gender partners than women. And in fact, you can even think about that if you think about literature. You know, the leader of the harem is always a man, and he's got lots of women. You know, in polygamous cultures, it's always the man that has multiple wives, not the reverse. Now, not surprisingly, this issue has been studied scientifically, I'll put in quotes, extensively. In one of the largest studies ever done, researchers from the University of Chicago interviewed 2,500 people at random over several years. They brought them in on many occasions to try to get the answer for the question once and for all. And they wrote this 700-page book called The Social Organization of Sexuality: Sexual Practices in the U.S. Actually, walking around with this book has proved to be a little embarrassing. Last week, my 11-year-old daughter saw it, and she goes, "Dad, why do you have this sex book?" And, I grabbed it back and I said, "That's for the course I'm teaching." I thought I'd gotten away with it, and everything was fine. And then later that day, she texted all of her friends about the new news that, what do you know, her dad teaches sex ed at MIT. Anyway, this study concludes that, on average, men have 74% more opposite gender partners than women. is one of their central claims. And this is in the US. Okay, now when you think about it, that sounds maybe reasonable. You know, might be okay. But not according to ABC News. They did a poll of 1,500 people in the country in 2004 and concluded that the average disparity is much greater. In particular, in this study, they said that the average man has 20 partners, I'm assuming over their lifetime, and the average woman has 6. And this gives a disparity of 233%. So ABC News did a smaller survey, says that it's 233% here. Much more than 74%. Now, ABC News claimed this is one of the most scientific studies ever done, and that there was a 2.5% margin of error. Now, we'll actually talk about what that means mathematically later in the term when we do probability and do study polling. Now, of course, I should also mention that ABC News is the one that said Al Gore won the presidential election in 2000, I mean. Now, the study is called American Sex Survey, A Peek Between the Sheets. That doesn't sound so scientific. And it was on TV, on Primetime Live in 2004. The promo for this is really good. It says, a groundbreaking ABC News Primetime Live survey finds a range of eye-popping sexual activities, fantasies, and attitudes in this country, confirming some conventional wisdom, exploding some myths, and venturing where few scientific surveys have gone before. By the end of today, we're going to agree with that last statement. Okay. Now, who do you think's right? University of Chicago? Who votes for 74% as being pretty close? A few of you? I've already sort of slammed these guys. Who votes for ABC News as being more accurate? Yeah, nobody. Who votes for No Way to Tell? I got some votes there. All right. So how do you tackle this problem? You know, in theory, we could do our own 6042 survey. I don't know how much we'd really learn, and for sure I'd get fired. So I don't think we're going to do that. But fortunately, this is the kind of question that can be handled and actually answered by graph theory. Even though it might be more interesting to interview thousands of people and find out what's going on, that's not as efficient as using graphs. So let me start by defining what a graph is. Informally, a graph is just a bunch of dots and lines connecting the dots. It's actually very simple. So here's a graph. These are the nodes, and they're connected with these lines that are called edges. And often the nodes and sometimes the edges are labeled. For example, we might call this x1, x2, x3, x4, x5, x6, and x7. All right, that's an example of a graph. Now, this being a math class, we've got to give a formal definition of a graph. And we'll usually use the formal definition. A graph G is a pair of sets, often called V and E, where V is a set of elements called vertices or nodes, and it has to be non-empty here in this class. And we'll go back and forth between vertices and nodes. Even in the text, we use both words interchangeably. And E is a set of two-item subsets of V, and they're called edges. So for example, over here in this picture, V is the set of nodes is x1, x2, x3, up to x7. That's the nodes. And E, the set of edges, is pairs, unordered pairs of vertices. So for example, x1, x2 is an edge. And it's the same as the set x2, x1. Doesn't matter the order here. Later, in a week or so, we'll talk about directed graphs where the order matters. x1, x3 is also an edge here. And so on. I think we've got, let's see, 1, 2, 3, 4, 5, 6, 7 edges in this graph. And the last one would be x5, x7. Edges are also sometimes written with this notation. x1 line, x2 is another notation. And then later, when you talk about directed edges, we'll put a little arrowhead on one end of this. Now, the definition of a graph is really pretty simple. Just think of it as dots and lines if you want. But there's often differences in how people define graphs. For example, in this class, we don't allow the empty graph, i.e. the graph with no nodes. So we're going to insist that every graph has to have at least one node in it. And that's just to make the theorems we're going to prove be true. Otherwise, there are some theorems that are false for the special case of the empty graph. But we don't require the graph to have any edges. In fact, it's possible you have a graph with nodes but no edges. For example, this graph, 3-node graph. So here G equals VE, V equals x1, x2, x3, and E is just the empty set. Now, for a general graph, when you do have edges, we say that two nodes, call them xi and xj, are adjacent if they're connected by an edge, namely if xi, xj is an edge. All right, so for example, x5 is adjacent to x7, but it's not adjacent to x4. There's no edge there. Closely related is the definition of incidence. An edge E, which is xi, xj, is said to be incident to its endpoints, xi and xj. Okay, so for example, if I labeled that as edges E, E is the edge x1, x2, and it's incident to x1 and incident to x2. Then we can talk about the degree of a node. The number of edges incident to a node is called the degree of the node. So for example, what's the degree of x5 over here? 3. So in this case, the degree of x5 equals 3. the degree of x7 is 1. These guys all have degree 0. There's no edges incident to them. Now, in this class, we're going to look at only simple graphs, at least for a while. A graph is simple if it has no loops or multiple edges. Now, a loop is an edge that only connects up one node. That's a loop, and we don't allow it. A multiple edge is where you've got two edges that are really the same, that connect the same endpoints, also called a multi-edge. And those we're not going to have in simple graphs. We don't allow this. We don't allow that. Any questions so far about what a graph is? OK. So, all right, how are we going to use a graph to model the problem of opposite gender partners? That's the question we're after. So, any thoughts about what the nodes of the graph are going to represent? What is it? People. Yeah, so we're going to have people. And in fact, there's two kinds of people here. There's men and women. All right, and we got nodes here for the men. And in fact, in America, there's a lot of nodes here. All right, and so this might be, oh, I don't know, say that's Tom Cruise and Nicole Kidman. Now, what's the edge going to represent? Partners. All right, they were opposite gender partners. And there's actually more edges probably here. You know, we could have Penelope here, and Katie here, and well, probably lots more. I probably don't even know them all. And Ben's over here with Nicole, and Nicole got Jude and Keith. There's actually a website you can go to get a lot of these things here. And Katie went with Josh. It's called whosdatedwho.com, and you get a big graph. You can start filling in the edges. I don't know how reliable it is. Now, it's really critical that we're only looking at edges from here to here. All right, so if there's an edge between Tom and Ben, I don't want to know about it. All right, so just opposite gender partners. OK, now, in the USA, the number of nodes here is about 300 million. All right, about 300 million people. And the number of men nodes, male nodes, call these VM, and this is VW. By the way, I'm using cardinality notation. When I put bars around a set, that is denoting how many are in the set. In the US, there's about 147.6 men out of the 300. And the number of women, oh, got a W here, is about 152.4 million. So there's a little bit more nodes on this side of the graph than that side in the US. What about the edges? Any idea of how many edges there are here? We don't know. I sure as heck don't know, how many edges there are. So that we don't know. The cardinality of the edge set we don't know. And we're not likely to figure out. I don't even think these surveys really can estimate that. But what we are trying to figure out is the ratio of the average degree of the men to the average degree of the women. Because the number of opposite gender partners you have is your degree here. And you're looking for the average guy degree compared to the average female degree here. That's what we're after. All right, so let's define that quantity. Let's let A sub m equal the average number of opposite gender partners for men. And we can let AW be the same thing for women. All right, now we're trying to figure out, to answer this question, what is AM, the average guy degree, over the average woman degree? And in particular, the University of Chicago says, they say it's 1.74, that the average guy has 74% more opposite gender partners than the average woman. ABC News says it's 3.33, that it's 233% more for the men than the women. Now we're going to figure this out, what this ratio is. All right, just use a little bit of math here and a little bit of graph theory. So let's write a formula for AM. Well, we're trying to figure out the average degree over here. Well, that's pretty simple. We just add up all the degrees and divide by the number of nodes. And that'll give us the average degree. So the average degree is the sum of the degrees over all men, x in the set of men, of the degree of x, divided by the number of men. All right, can somebody give me a simpler expression for this? It doesn't have that nasty sum in it? E, cardinality of E. I'm adding all the degrees here. Well, that's just another way of counting all the edges, because every edge shows up once and only once in a degree count here. And this is where we use the fact we have opposite gender partners, right? Because if I had some edges over here, they wouldn't get counted in the sum of the degrees here. All right? So this is just the cardinality of the number of edges divided by the number of men. Any questions about that? Because this is an important statement about graphs in general. When I have a graph like this, which is called a bipartite graph, we'll talk about more a little bit, but where the edges go from the left to the right, if I sum the degrees on the left, I'm just counting the number of edges. All right. Let's figure out a formula for the average number of partners for the women. Well, that's simple. That's just sum x over the women, the degree of x, divided by the number of women. Let me rewrite that so it's clearer. What's a simpler expression for this? Yeah, this sum, adding the degrees of the women, is just the number of edges, right? So that is cardinality of edges divided by the number of women. All right. Well, now we can solve for our formula, average over men over average of the women. That's E over Vm divided by E over Vw. Wow, this is nice. I don't know what the number of edges is, but it just canceled out. And this is just the number of women divided by the number of men. And in fact, we know that that's this number divided by that number, which is about 1.0325. So we just proved that on average, a man has 3% or 3.25% more opposite gender partners than women. No need to do the interviews or spend years doing it. That is the answer. And it has nothing to do with the promiscuity of men or women. Nothing at all. All right? So the Chicago study is way off, and the ABC News study is completely nuts. It just can't be right. This is a proof. All right, now, what happened here? Well, what's going on? What's the reason for why this is true? Yeah?
Well, if a male has a female partner, then a female has a male partner.
Yeah.
And you're not looking at like how many males are going to one female. Like the promiscuity isn't even like a part of the question.
That's right. You're just, it takes two to tango, right? Every time you got a guy, you got a woman, and you have the number of relationships going. The average for the men is that number divided by the men. Average for the women is that same number divided by the women. And so if there's more women, they're going to have less partners on average. Has to be. So it really was a stupid question. It's very, very simple to answer. Now, as it turns out, there are endless studies like this in the literature. In fact, a few years ago, the Boston Globe ran an explosive story about the study habits of students on Boston area campuses. And their survey showed that, on average, minority students tended to study with non-minority students more than the other way around. All right? And they went on great length consulting the experts as to why this might be true. Why is it that minority students study with non-minority students more than the other way around? Now, can anyone tell me why it is certainly true and not surprising why that's the case? Because they're a minority. There's fewer minorities than non-minorities. End of story. We don't need this sociology PhD from down the street to explain it to us. All right. We're going to see a lot of other bogus studies later. This is not unusual, especially when we get to probability. Just every day there's a new one in probability. Any questions about this before we leave? Unfortunately, that's most all we'll say about sex today. Okay. Now, in this example, we used an edge in the graph to denote some kind of affinity, between two nodes. The two nodes liked each other in some sense if they were connected by an edge, or they had a relationship of some kind. There's lots of examples in computer science where you use an edge to denote just the opposite, that the two nodes can't be near each other or don't like each other. For example, consider the problem of scheduling final exams at MIT. And they do this after they find out all of your schedules. And they try to schedule the exams so that you don't have to take two at once, or there's as little of that as possible. For example, let's do an example here. Say we look at these 5 classes. Take 6041. And this may not be totally accurate, but roughly. So I've got 5 MIT classes, and I'm going to put an edge between pairs of classes that have overlapping student enrollment. So in this case, for example, we've assumed in drawing this graph that you can't have our exam the same time as 6002, on the assumption there's students in both classes. But you could have our exam the same time as 6034, because there's not an overlapping student, or a student in both classes. So the exams could be scheduled at the same time. So we've used a graph to represent which courses can't have their exam at the same time. Now let's also suppose we have a set of slots for the exam. And say they're all on a Wednesday. And the first slot is Wednesday from 5 to 7. And the next one is 7 to 9. And then the next one is 9 to 11. And then 11 to 1 in the morning. And then 1 to 3. pretty late. And your job is to figure out how not to have to use these later exam slots. You'd like to use as few as possible so you're not, going too late at night or come before the holidays so you're not having exams on Christmas and New Year's, for example. So the goal is to assign slots to the nodes. Put every node in a slot so you don't have nodes hooked by an edge getting the same slot. Now, this is an example of what's called a graph coloring problem. So let's define that. Given a graph G and K colors, assign a color to each node so that adjacent nodes get different colors. All right, and then the minimum number of colors you need is called the chromatic number of the graph. So the minimum value of K for which such a coloring exists is the chromatic number of the graph. And it's denoted by the symbol chi of G. All right? Because usually you want to use a small number of colors. Now, what does a color represent when we're dealing with this problem? What's the meaning of a color? A time slot. Okay? So let's call this time slot C1, C2, C3, C4, C5. So there's 5 possible colors. Now, of course, we could color this graph with 5 colors. Every node could just get its own color. But then somebody's taken their exam, from 1 to 3 a.m., and, that's a bit of a pain. Let's see if we can do less than 5. Let's say I give this color 1. And let's give this one color 1. That's OK, because they're not connected. I can't give this one color 1, so I give it color 2, say. Now this one I can't give color 1 because this guy got it. He can't get color 2 because that guy got it, so I give it color 3. And, well, I can't do 1, 2, or 3 here, so I got to go to color 4. All right, so 6042 will get the 11 p.m. to 1 a.m. slot. Not so good. Can we do any better? Can we get away with 3 colors? Some say yes, some say no. How many people think you can do 3 colors on this graph? A bunch. How many think you can't do any better? All right, the vote is mostly for 3. Well, let's see. Any ideas? Anybody see how to do 3? Yeah?
Sign C4 to 6034.
Sign C4 to 6034.
Or C1 to 6042. Probably.
I can't do C1 to 6042. It crashes, but can I do, yeah?
Put C1 at 6003.
C1 and 6003.
And then get rid of C1 and 6034.
Get rid of,
Change it to C2.
make this a C2. Oh, yeah. All right, these got C1, they're not adjacent. These got C2, they're not adjacent. This can now get C3. So we can have our exam from 9 to 11, which is better. All right, can anybody do it in 2 colors? All right. Can anybody offer a reason why 2 colors may not be possible? Yeah?
Because let's say you could do it with 2 colors.
Yep.
6041 and 6002 have to be different colors.
Yes.
You'd say C1 and C. 6042 can't be C1 and it can't be C2.
Yeah. Good. So you can't do 2 colors because these 3 guys would violate that. You got a triangle here. Each one of these guys has to be different than the other 2. So 2 colors can't work. You got to have at least 3 in this case. So 3 is optimal. We have just shown that for this graph, the chromatic number is 3. All right. Now, in general, doing what we just did is very hard. No one knows a fast algorithm for determining the chromatic number. In fact, it's a weird kind of problem because it's easy enough to check that a coloring is OK. If somebody put a coloring on the board, you can check, oh, that works really simply. You just check every edge and make sure the colors are different. But figuring it out, as best we know, you got to try an exponential number of possibilities. So if I had 100 nodes here, my running time of the algorithm to check all the possibilities would be exponential in 100. Yeah?
The highest degree of each node or nodes?
No, but it's no worse than something like that, as we'll see in a few minutes. That's a great observation, and we're going to come back to that in a few minutes. But it's not just that. OK? Now, in fact, even figuring out for an arbitrary graph if 3 colors can be done, called the 3-coloring problem, that's really hard. No one knows how to solve that in less than exponential time. In fact, it's called one of these NP-complete problems is what it's called. How many people here don't know about NP-completeness? Is everybody? All right, so a lot of you haven't seen NP-completeness. OK, so there is a class of thousands of problems. In fact, there's books that list these 1,000 problems that are all NP-complete. Somebody's proved they belong in the class. And what that means is that if somebody gave you a solution, like a coloring here, it's easy to check really quickly if it's valid. But figuring it out is really hard, and if you figured out how to solve one of those thousands of problems, like suddenly you figured out how to tell if any graph could work with 3 colors, you would solve automatically all other thousands in the book. So it's this book of problems you will constantly run into in your career in computer science. And it's bad when you run into one because there's no good algorithm to solve it known. But if you just solved one of them, the other thousands would suddenly be solvable quickly. Even better, you win $1 million prize, one of these Millennium Prizes we talked about in the first lecture. Even if you show you can't find a fast algorithm for one of them, that means that none of them have fast algorithms, and you also get $1 million. So this is the central problem in computer science, in theory of computing, is whether or not you can solve these NP-complete problems. Now, actually, lots of people have claimed to do it. And in fact, there was a lot of buzz in the community about a month ago when actually a reputable researcher at HB Labs said he'd done it. He'd proved that you can't solve NP-complete problems. And he got people going for probably at least a week until they discovered a fatal flaw. And the proof was actually bogus. So no one still knows if you can solve these NP-complete problems quickly. Now, the problem is, in practice, you run into these things all the time. Like MIT really does have to schedule the exams. So you got to do something. You can't just go say, hey, it's NP-complete, so no exams this year, or whatever. That's not going to fly. You got to do something. So now this is a problem. Many of you, when you go into careers, are going to be faced with this. You got to do something. Any thoughts about an algorithm for coloring graphs that might use a small number of colors. It doesn't have to always work, or you're going to win a lot of money if it does, but a simple algorithm, you can't take e to the 100 steps. You got to be linear, probably, or quadratic time. That could get you a small number of colors. Any thoughts about what you'd do? Yeah?
Number of degrees of a node.
The number, what about it?
Like the highest degree in that node for 6442 is degree 3.
Yeah?
So you can use that.
Good. All right, but so what do I do with that information? I found a node with high degree. There's three of them that have degree 3 here. What do I do with them?
Pick a different color.
Pick a different color. That means I've colored some of the others. If I pick a different color, do I start with them or do I finish with the high degree nodes? Because you got to assign the colors to them. And high degree is important to be thinking about. We're going to prove a theorem in just a minute about related to degree and coloring. Start with them. And do what with it? Color it?
Yeah, and then assign the ones that aren't connected, if hopefully you can, to the same slots.
Okay, so I could, here's a degree 3 node. I could start with color 1 for that. And then what do I do next? I pick, its neighbors have to get different colors, I guess. You'd start coloring the neighbors.
Well, I guess I would, my first instinct would be to color all the ones with the most degrees first.
Okay. And what color would you use for them? Different ones, if they're connected, or if they're not connected, you'd still use different ones?
Only if they're connected.
Only if they're connected, use different ones. And so if they're not connected, you use the same colors? Yeah? All right, so this is actually, you're getting close to an algorithm that actually works pretty well. The underlying principle you're sort of thinking about here is you've got some notion of the order in which you're going to process your graph. And you're going to start with the high degree nodes in your case. And as you go along, you're going to start coloring the nodes. And you're going to make sure you color them legally. And it sounds like you're going to color them with a low color, all right, as you go along. And that is probably the most basic graph coloring approach. And you could almost say is a generic approach. So let's define that and then prove some facts about it. Most of the graph coloring algorithms in practice are based on this approach. And we're going to call it the basic graph coloring algorithm. And for a graph G with vertices V and edges E. So the first step is going to be to order the nodes from 1 to n. Now, in your case, you were suggesting an ordering where I have the high degree nodes first. All right? But for now, we're not going to specify that. We're going to make it any ordering you want. And then we're going to have a notion of an order on the colors as well. And I don't know how many colors, but they're going to be numbered 1, 2, and so forth. And then we're going to process the nodes one at a time. Up to n. We color the node. So at step I, we color the ith node v sub I with the lowest legal color. And by legal, I mean you don't color at the same node as another node that's already been colored that it's adjacent to. All right, so let's try this. In fact, this is sort of the algorithm I used initially to color the exam graph over there. All right, so let's look at that. So let's say let me erase the colors here. and put an ordering on the nodes. So let's say I ordered them with 6034 first. So this will be V1. Then 6041 is V2. Then V3, V4, V5. If that's my ordering, what color would I assign to 6034? 1, C1. I'd color it first to get C1. What color does 6041 get? C1 as well. It's the lowest possible color that's legal, and it's not hooked to this guy, so C1 is legal. What color do I give here? C2. Then I color this one next. Can't do C2, can't do C1, so I pick C3. And then I get the 6042 last, and I can't do 1, 2, or 3, so I do 4. All right, so this algorithm with that ordering gave 4 colors. However, we know there's a way to do a different ordering that gives us 3 colors. In particular, let's see if we do this. What happens if we use this other ordering? Erase these. Say that's V1, V2, V3, V4, V5. Now I get C1. This will be C2, C1. What's this one get? C2. Oh, much better. C3. So different orderings result in different numbers of colors here. So the whole art now becomes finding a clever ordering. And some people have already had good ideas. Pick the largest degree nodes first. And in fact, if you simulate the algorithm on lots of graphs, you do better on average when you color the large degree nodes first. And then if you start to use more exotic orderings, you can do even better if you take a lot of graphs that are out there and run your algorithm and see how well you do better with more sophisticated orderings. In fact, this was my senior thesis back when I was an undergraduate student, was trying to figure out better and better orderings that worked for graphs. And at the time, it caused a bit of a problem. I was an undergraduate at Princeton. And Princeton, to this day, I think, still has exams after the holidays, the Christmas holidays, New Year's holidays. And the students wanted to have the exams before Christmas because they hated going home for the holiday, and then you got to worry about your exams when you come back. And the faculty said, no, there's no way to get them all compressed into a small number of days. Now, I wasn't aware of all that at the time, but my thesis was go figure out good ordering. So I tried lots of different orderings, and I tried the largest degree first, and recursive versions of that actually work very well. And then tried it on the Princeton exam graph. And lo and behold, you could actually squish it down so you could give all the exams, I think it was 4.5 days. Plenty of time to give them before Christmas, which caused a fair scandal at the time because then the faculty had to come clean that they just didn't want to bother having the exams before Christmas. Now, this algorithm is an example of what's known as a greedy algorithm. Now, in a greedy algorithm, it's always simple. You just go one step after the next, taking the best you can do at each step. You never go back and try to make things better. You never do hill climbing. If you're familiar with that term, you just always keep it simple, one thing after the next, very fast. Sometimes works great in practice. Sometimes doesn't. But it's always where you'd start, some simple approach like this. Now, this algorithm actually, even if you don't try to monkey with the ordering, even for a worst case ordering of the nodes, actually does pretty good for a lot of graphs. And in fact, it does really well, as somebody already asked about, if all the nodes have low degree. So let's state that as a theorem, and then we're going to prove that. So if every node in a graph G has degree at most D, so that's the biggest degree in the graph, D, then this basic algorithm uses at most D plus 1 colors for G. No matter what the ordering is, you'll never do worse than D plus 1 colors. So what's the value of D for our exam graph over here? D is 3. Every node has degree at most 3. And so it says that no matter what ordering you picked here, you'd get at most 4 colors. Now you might do better. In fact, we found an ordering that got 3. So it's possible to do better. So let's prove this fact, because this makes a difference. Say you have a graph with hundreds of nodes, but every node has degree at most 3. Well, that says you only need 4 colors, even if the graph has 1,000 nodes. And that's very useful. So in that kind of situation, it does very well. So let's prove that. Any ideas as to what proof technique we're going to use? Invariant, close. Not quite an invariant, but close. What? You know, well, ordering principle, yeah, we're going to use the equivalent version of that. We're going to use induction. I'm not a, if you like well, it's equivalent to well ordering. So if you like well ordering, you can do it that way. I think it's easier using induction here. So the proof is by induction. All right, so the first thing we need is an induction hypothesis. Any thoughts about what the induction hypothesis should be? Yeah?
If you have a graph with n nodes, then where the degree of any node is less than or equal to D, then you can do it in at most D plus 1 colors.
That's great. You're going to do really well in the midterm because you put an n into this thing. But there's not an n here to start. What are most people going to do? We used to ask this actually. We asked this once on a test many years ago, and it was an utter disaster. Because what did everybody do? Maybe one student or two put an n into here. But what's the natural thing to do to induct on here when you look at this statement? You're going to induct on D, right? Because the first thing you do is you make this be your induction hypothesis. There's only one thing to use. So you're going to have your predicate be P of D, and it's going to be that. Now, it didn't occur to us that's what everybody was going to do. It should have. They all did that, and it was a disaster. Because if you do this, well, you've got to take a graph with maximum degree D, or D plus 1 in the inductive step, pull out all the nodes with degree D plus 1 to get a graph with now degree D. And that's a mess. You just pulled out a lot of nodes, potentially. Color that in D plus 1 colors. Now put all that junk back in and say you only used one more color? Nightmare. And these are MIT students under pressure. That was a nightmare. So that does not work. And in fact, we will ask an induction question on graphs on every test you take in this course. All right, it will happen. And so usually, with induction, you take this as your induction hypothesis. With graphs, you have to be careful. And the worst part about this is we tell people when this doesn't work, use a stronger induction hypothesis. So students tried to make it stronger, but they're still stuck on D, and it was still a disaster. With graphs, you do something different. And the first thing you do with a graph usually is put n in here. And if it doesn't work with n, the number of nodes, you put in e, the number of edges, and induct on that. And so what you said is exactly the right thing to do. Don't do this, or at least don't spend too much time on it. Pretty quickly try this. If every n-node graph, if every node in an n-node graph G has degree at most D, then the basic algorithm uses at most D plus 1 colors. And now you induct on n. And almost always in graphs, that's the first thing to try, even if it's not in your theorem statement. Any questions about that? All right. Well, let's start with this and see if we can make this one work. So what's the next step in our proof? What do we got to do? base case. And the base case will be not n equals 0, because we can't have a 0-node graph, but n equals 1. And how many edges do we have? 0. If there's one node, we don't allow loops, so it's 0 edges, which means that the degree of our graph has to be 0. There's no edges. And of course, there's only one node, so one color is going to work, and that happens to equal d plus 1. All right, so the base case is true. For one-node graphs, you can always use d plus 1 colors, where d is the max degree. All right, next we have the inductive step. So here we assume Pn is true for the induction. And now we look at an n plus 1 node graph to show Pn plus 1 is true. So we let G be any n plus 1 node graph. We've got to show it, you can color it in d plus 1 colors. And let's let d be the max degree, the largest degree in G. We've got to show we can color it in d plus 1 colors. Well, the basic algorithm, let's see. First thing we do is we order the nodes in an arbitrary order. And we're going to show whatever order you pick is OK. All right, so order the nodes. Any way at all. Now, how am I going to use the induction hypothesis? I know I can assume that for any n-node graph, I can color it in the max degree plus 1 colors. How am I going to use that to help me color G here, the n plus 1 node graph? Any thoughts? Yeah? Yeah. Let's create an n-node graph by looking at these nodes and taking this one out for the time being. Remove the last vn plus 1 node in the order. That leaves an n-node graph. All right, so let's write that down. We remove vn plus 1 from G. And that creates a new graph. Call it G prime with vertices v prime and edges e prime. So we create a new graph by removing that node. And we remove all the edges tied to that node. So for example, over here, let's see, the last node was 6042, so we take out 6042 and all these edges. And this is the graph that we're left with. That graph has n nodes. What's the maximum degree in G prime? When I pull out a node, can the degree of any node go up? No, I'm just taking stuff out. So I know that G prime has maximum degree at most d. The degree didn't go up of any node. Might have gone down, but it didn't go up. So G prime has max degree at most d, and it has n nodes. So we can use the induction hypothesis, Pn. It says that the basic algorithm uses d plus 1 at most, d plus 1 colors for nodes V1 to Vn. Any questions about that? So if this were the n plus first node, the last node in the ordering, take it out. The basic algorithm now would take the same order here, V1, V2, V3, V4. Basic will color that in D plus 1 colors. And all I have left is to give this guy a color. And I'll have color G. Question? Oh. All right. So by induction, I've colored these guys, V1 through Vn in D plus 1 colors. All that I have left to do is color Vn plus 1. And hopefully, we're not going to use color D plus 2, because then it wouldn't work. We got to use one of the first D plus 1. All right, so let's look at Vn plus 1. And let's call its neighbors in G U1, U2, UD. It has at most D neighbors because every node in G has at most degree D. A neighbor is a node you're adjacent to. All right, so Vn plus 1 has at most D neighbors, is adjacent to at most D other nodes. Now, what does that mean about the color I can use on Vn plus 1? What do I know about what color I can use for that?
D plus 1.
Yeah.
It can't be any of the colors of U1, U2, so on.
It can't be any one of these colors that were assigned here. That's true. So how many colors got ruled out? At most D. And how many am I working with? D plus 1. So I got one left that I can use safely. Okay? So this means there exists at least one color in my set of D plus 1 colors that's not used by any neighbor. And we're going to give Vn plus 1 that color. All right, so now I've colored every node in G, the n plus 1 node graph, safely, using a total of D plus 1 colors. All right, so that means the basic algorithm uses at most D plus 1 colors on G. That means Pn plus 1 is true. Whoops. And the induction is complete. Any questions? Yeah.
Could you also say start from the other way and start with like 1, go to 2 nodes, 3 nodes, at each step keeping all nodes connected to all other nodes, and then you could also see the same thing that you're never going to be using more than equals 1 colors.
What do you mean by keeping all nodes connected?
Or all incident to each other. Something like VS4, each node has an edge connecting to each other one.
Okay, so then I get a specific graph. I start with this. I add a node and make it adjacent. I add a node and make it adjacent.
But it's 3 nodes, the max degree is 2.
Yep. So you've constructed a particular graph. This is actually called, for the n nodes, it's called Kn. Is the n node complete graph. Also called a clique, like a clique of friends, where everybody likes everybody in a clique. And in fact, for n here, if there's n nodes, what's the max degree? Max degree is n minus 1. What's the chromatic number of this graph? What's the minimum number of colors?
N minus.
N. They all have to be different, which is d plus 1. So you have built a special graph for which the optimal number of colors is d plus 1. But that is not a proof that this is true for all graphs. Because you've looked at a particular graph here. What's that?
You add, it means that you can still use your less than or equal to sign.
I see. So you'd add a node, and it's only connected to a few of them.
No, it's connected to all of them, but it still implies that you need less than or equal to the colors. It turns out it happens to be equal to.
Yes, in this case, that's right. So you've made an argument for this case where it actually is equal, but that only worked for this graph. It is the worst case. So it meets the bound. It shows you cannot improve this bound. Yeah, is there a question up there?
That's all I was going to say, is that you could prove that it was the worst case.
Right, so what you've done here is you've shown that I could not make that theorem any stronger. I could not replace it with D here, right? Because you give an example where I can't get D colors, where the maximum degree is D. But that doesn't, to get a proof of the theorem, I got to go through all this. That wouldn't give me a proof of the theorem. They're not equivalent. One's an upper bound, one's an existence of a lower bound. This shows that for any graph, you need at most d plus 1. So any graph at most. That shows there is a graph that you need at least. And they are not equivalent. All right? One is for all an upper bound. The other is there exists a lower bound. So different in two ways that are important. All right, this kind of proof is very typical for what you'll see with induction and graphs. And you'll get a lot of practice with it. Are there any other questions on this proof? OK. All right, so we've seen now by that example that we can't improve the theorem. In some cases, though, the theorem is way off for some graphs. Can anybody think of a graph where the bound we get from the theorem of d plus 1 colors is way off from the actual chromatic number you need, the number of colors you need? Yeah? What is it?
A graph like the one we got, we have like all men and women, like two sets of vertices and all the edges going from the left to the right.
Good, OK. Yeah, so what if we did this graph? Let me draw that. So you've got a bunch of nodes here, a bunch of nodes here. And every node here is connected to every node over on the other side. And if this is an n-node graph and I've got n over 2 on each side, what's my degree here? What's my max degree of this graph? N over 2. So D is n over 2. What's the chromatic number? How many colors do I need for this? 2. All right, so D plus 1 is way off of 2. There's an even worse example. Yeah?
You have one node in the center that's connected to a bunch of nodes radially distributed about it.
Yeah, the star graph. All right, so I got 1 in the center. I got n minus 1 outside. So here the maximum degree is n minus 1, just like a complete graph. But how many colors do I need? 2. So it's even worse here. All right, now what about the basic algorithm? How well does the basic algorithm do on this graph? Order the vertices some way. Color them one at a time, the lowest color. How many colors is it going to use? 2. In fact, it doesn't matter how you order the vertices. V1, V2, V3, V4. Because I'll color this one 1. What am I going to color that one? 1. Then I get to the center. What am I going to color it? 2. And now all the arms, what do they get colored? They all get 1. Whatever order you pick, you get 2 colors. All right, so now there's a difference between the theorem just gives you an upper bound. It says at most d plus 1 colors. But in fact, the algorithm can do a lot better than that, as on this example. So the algorithm might be a lot better. Everybody see that, what we're doing here? How the algorithm is better than the bound we proved by the theorem, even though the bound was pretty good for some graphs. Now, it turns out, we're not going to win $1 million for this algorithm. And in fact, this algorithm is sometimes very bad. And a really bad example is very close to this. In fact, actually, this one, let's look at how well does BASIC do on this one? Here. Make some ordering. V1, V2, V3. What's the BASIC algorithm going to do on this we call it a complete bipartite graph, is what this is called. I'll define bipartite in a minute. But what's the BASIC algorithm do here? Any idea of how, does it take n over 2 colors, or does it take 2? Any ideas? 2. So take a vertex, and the first one, say V1's here. It gets C1. As long as I keep picking vertices over on this side, they're going to get C1. As soon as I get to a vertex over here, what color does it have to get? C2, because it's touching the very first one we had here. So when I get vertices over here, they're all going to be C2. When I go back over here, they're going to be back to C1. So actually, BASIC does good here too. Gives you 2 colors. Yeah? And those two aren't connected. But in this case, if I've got a vertex over here, it is by definition connected to the vertex over here, because every possible edge is here. But that's a great idea. What if they weren't all connected? That's actually a great idea. Let's, in fact, the nasty example for the BASIC algorithm is very much like that. Let's draw it. Because so far, the BASIC algorithm is pretty much done perfectly on all the graphs we looked at, even when the theorem wasn't tight. So here is a nasty graph. And it is very close to the graph we just looked like, where all the edges are there. In this case, all the edges are there except for the one straight across. So if this is, the edge denotes likes, this is a world where you like everybody but your spouse. All right, so you have an edge to everyone except the one directly across from you. No edge there, and so forth. So it has almost every edge, but it's missing these edges. Now, the BASIC algorithm might do well here. What would be a good ordering for this graph? To label these V1 through Vn? Yeah?
Go through everything on the left side, everything on the right side.
Yep, that's right. Because then, color 1, color 1, color 1, all the way down. One color for the left. What does this one get? Color 2, because it's hooked up against. And these all get color 2. So I've used 2 colors. Really good. BASIC algorithm's looking great. Now here's a harder question. Can you figure out a bad ordering for this graph, where I use a lot more than 2 colors? What is it?
Starts at the top, goes across, then to the next level, and then across.
Very good. V1, V2. Just as natural, really, if you think about it, to order it this way. All right. What color does V1 get? C1. What color does V2 get? C1, because it's not hooked up here. What color does V3 get? C2. What about V4? C2. It's not hooked up. It can't get 1, because that's up here, and it's not to 2, so it gets 2. What color does V5 get? C3, because it's hooked up to 1 and 2. V6? C3. It's hooked up to 1 and 2, but not 3. And you can see what's happening here. All the way down here, he's hooked up to all the n over 2 minus 1 colors. So we have to take Cn over 2. So if you picked that ordering, not so good. You use n over 2 colors. So it really matters the ordering. Now, I should say graphs like, actually, any questions about what we did here? About this? All right, now I should say that graphs like this have a special name. They're called bipartite graphs. And that's important to remember. All right, so a graph is a graph G is said to be bipartite if the vertices can be split into 2 sets or partitioned. We'll call them a left set and a right set, so that all the edges connect a node in the left set to a node in the right set. So in fact, a lot of today we've been looking at bipartite graphs because the nodes are here, like the men and the women, and the edges only go from the left to the right. And then it's called bipartite. And it's called bipartite because you can do it with 2 colors. They're in 2 pieces. So you don't win $1 million for deciding whether or not a graph can be colored in 2 colors. That's easy. You'll even do it for homework one of these times. You do win the $1 million for deciding if a graph can be colored in 3 colors. That's really hard to do. Now, coloring problems come up in all sorts of applications. You know, this company Akamai that came out of MIT we've talked about, we run a network of 75,000 servers. And they're used to distribute content on the internet and so forth. And we have to deploy a new version of our software on those servers pretty much every week. We're pushing new software out. And you can't deploy on every server at the same time because you got to take down a server to deploy new software on it. You've got to take it out of commission. And so we can't just take down all 75,000 servers because then all the Facebook and Netflix and all those sites would stop. That would be bad. And we can't do them one at a time because there's 75,000 and it takes a few hours for each one to go get the traffic off, stop it, load new software, and turn it back on. And it would take us years to do one software install, which we got to do every week. So we got to figure out a schedule for how many servers you take down at a given time and which ones. And it turns out pairs of servers have certain critical functions. So there's certain pairs of servers you can't take down at the same time. So we have a gigantic 75,000 node coloring problem, where there's edges between servers, nodes are servers, and there's an edge between them if you can't install new software at the same time. And so it turns out when you run one of these graph coloring algorithms on it, you could do it with 8 colors. It just turns out that way. So that means there's 8 waves of install that go on to the network. And now 8 times a few hours each means that we can do it in a day and you can manage it. You know, on a much smaller scale, the same problem exists for register allocation, for variables. Here you got to assign every variable to a register, but you can't have variables that are active at the same time associated with the same register. And you want to minimize the number of registers you need. So again, you have the graph coloring problem. The number of colors is the number of registers you need. And two variables can't get the same color if they're active at the same time, so you put an edge between them. The most famous example of graph coloring is the map coloring problem with the four coloring theorem. And so here, every country is a node. Adjacent countries have an edge between them, because you don't want to color adjacent countries the same color, or you can't tell they're different countries. Now, the last example we could talk about is an important problem in communication theory, communication networks, where again coloring comes up. Now here, you need to assign frequencies to radio stations or to cell towers. Comes up in mobile networks or just with radio stations. And if two towers have an overlapping area, they can't be given the same frequencies, or you get collisions between the towers. So suppose, and frequencies are very expensive. Companies pay the government a lot of money to get certain spectrum. So suppose you had this problem. Here's tower A, and this is A's range, where it reaches. Here's tower B, so it overlaps some with A. Here's tower C. Here's tower E. And here's tower D. All right, now the question would be, how many radio frequencies do you need? What's the minimum number of frequencies you need to enable all the towers here? Well, we can make that be a graph. There's a node for each tower, and an edge between towers if they overlap. C doesn't overlap with B. E does. E overlaps here, and then D overlaps here. So how many frequencies do you need for this graph? 4 would work. 3 is better. Can you do 2? No, you can't do 2 because you got here. But you could do 3. You could do 1, 2, 3, 2, 1. All right, this problem comes up. Did I screw up? Ooh, no, I can't do that. 1, 2. Yeah, much better. All right, this problem comes up all over the place. You will certainly see it sometime in your career. You'll have some problem where you're scheduling something, and it's really a graph problem in disguise. OK, that's it for today.